and hello, welcome everyone to this video of turbulence modeling. So actually there is some updates again. I've taken a long hiatus from this series for good reason, because getting buoyant pimple foam to work was so frustrating. However, there is some light at the end of the tunnel. Okay, so let me again search for the paper, jet impingement. Yes, never mind. I'll just skip the all of this. But I want to point you to this paper by, I think, Dewan. This guy. I don't know how to pronounce his name properly again. So sorry if I butcher the name. I didn't pronounce properly. But it's very good content. One of the important things is that you use open foam for jet impingement. So I kind of covered this in my open foam heat transfer series, but since I don't assume any of you actually watched that, I'll just go ahead and explain. One of the things is that they use this open foam solver called buoyantPimpleFoam pimple foam, which uses the boussinesq assumption. And what it means here is that you're kind of limited in a sense that your Prandtl number cannot change with temperature. However, this actually plays well for solvers, or it plays well for cases where there are sudden fluctuations in velocity, such as large eddy simulation. Okay, now I tried this and it gives very promising results. However, they are not 100% physical, and I'll show you why shortly. Okay, so this is the case that has been running, and it's been running for about 7 seconds. If simulated time. So I've been running over a few days, or almost a full day already, and the results are promising. Okay, so what's actually going on here? Okay, so let me show you. Okay, CD experimental IDDS case. Okay, boussinesq. So this uses a boussinesq approximation, and it actually ran a lot longer than 0.145 seconds. However, I mean the result summary is this: it runs a lot longer than 0.145 seconds, as we know that the buoyant pimple foam kind of crashes around that point in time. However, it's able to run past that, but after you run it for a longer time, again the results do not make sense. Okay, so they do not make physical sense, so it's kind of a not complete success, but it's a good direction to go. So it's actually probably due to a solver algorithm problem in OpenFoam that does not allow it to solve as well for buoyant pimple foam as compared to buoyant boussinesq pimple foam. Some of that you can go and watch my OpenFoam heat transfer series to look at more details as to what actually is going on. So you can see over here there'll be a heat transfer playlist, so just take a look at what that is, and you should go to, I think, one of the later videos. Just skip all of this. If you want to take a look at what the algorithm differences are, you can look for this video called Key Differences between buoyant pimple foam and the boussinesq version. So this is the video I would go for if you want to actually know what's going on behind the scenes. Okay, I'm using the OpenFoam ESI version. In OpenFoam 7 and 8, the OpenFoam.org version, as of this video, it does not have buoyant boussinesq pimple foam anymore. But there is a small workaround, but it involves turning off natural convection as well. So anyway, I have this case here, and let's show you what it looks like on ParaView. So let's see, turbulence modeling, and let's go to OpenFoam examples, experimental cases, and let's see, every solution, no, boussinesq, yes. So let's show you this thing. Okay, and it's not exploding. There are some results there, so that's actually pretty promising. Okay, so this is what it looks like initially, and this is what it looks like after 0.5 seconds. I'll rescale the velocity. So you see there's actually sort of a large eddies being formed. There are some velocity fluctuations, and this is actually pretty promising. Okay, and you look at the pressure as well, PRGH for example, rescale it. Okay, you can't see any differences here. Let's rescale. Yes, yeah, so there is a good pressure difference here that's driving the flow somewhat. So PRGH is not what is driving the flow, because you kind of take out the hydrostatic component. Mostly it's hydrostatic component that's driving the flow, and of course it's not the hydrostatic component. It's the FV options that we are giving it. Okay, so there is some gravity force there. Okay, let me show you the temperature profile. Okay, so this is what the temperature profile looks like. There's some I guess some boundary layer or what. There's a hot wall and a cold wall, and they are exchanging heat with the fluid. So at this point you can see it's still somewhat okay. You don't see very much heat being transferred into the fluid or taken out of it, but that's okay for now. So actually what it shows is that buoyant PimpleFoam, buoyant boussinesq PimpleFoam is able to simulate this right. And what actually happens is that if you again you have to do this, you have to run it for a long time, and what you'll see happening is this. Okay, what's actually going on over here? You see the temperature actually going to 5.2 minus 5.2 times 10 to 11 and 1.3 times 10 to the 12. So you see this is actually not working anymore. However, the velocity profile is still pretty reasonable, as you can see here, but it is not functioning the way it should be. There are numerical instabilities, and normally buoyant PimpleFoam would crash if the temperature goes below 0 Kelvin. Buoyant boussinesq PimpleFoam doesn't do that. It will keep solving and solving, but you can consider this case sort of failed. But hey, it shows you that the differences in algorithm does make a huge difference in how you get results. Okay, so I'm gonna stop this, and I will just clean this up. So let me rename this as boussinesq. I'll rename this as promising experiment. IDDES case boussinesq. Alright, so I want to git add promising blah blah blah, and that should do it. Okay, git status DUSH 215 max. Okay, so let's do the experimental IDDES case boussinesq. Okay, so all of this I want to delete. Alright, I don't delete this because I want to kill this process. So okay, I have not killed this process yet. Yeah, I did, I think. Okay, RMS-RF experimental IDDES case boussinesq. Alright, so that's about it. Promising experimental case here. Alright, so oopsie, git reset, git status. Yeah, you see I've been doing lots of things in the background. Okay, So let me git add again and git commit boussinesq case has promising results. And one other thing I found was that changing the density to be constant actually allows buoyant pimple foam to solve for it allows buoyant pimple foam to solve for the case pretty well. So let's go CD experimental IDDES case 2, thermophysical properties modified. Okay, so there were a few things to take note. Actually, you note that some things to note are that normally internal energy, this is just the open foam technicality, but using sensible internal energy is much better for liquids. So let me see where that is. Where is it? HE. Alright, so okay. So over here is we see there's a runtime selectable energy solution variable. Okay, blah blah blah. Okay, E is the preferred form of energies for fluid. H is the preferable form for steady state and some classes of transient gaseous problems, especially combustion. So actually using internal energy as a way to solve, it tends to be more stable for the algorithm. So I actually tried changing that in the thermophysical properties to sensible internal energy. Okay, and that didn't work out very well. Okay, so let me do block mesh. Okay, let me do. Do I have an all run parallel? Yes. And let me put a script here. Okay, so I'll just run block mesh or run application block mesh. Block mesh with the dictionary system block mesh dict IDDES. Then I will just run in parallel. So let's do an all run parallel and see what happens. So if we take a look at the I'm going to delete this, I'm going to close this up. If you take a look at the we see that the thing crashed. So take a look at this _f log, we see the log.buoyantPimpleFoam. Okay, log buoyantPimpleFoam. Apparently the solver crashed after a few seconds. Why did it crash? Reason is there are again numerical instabilities. There's a so-called number of iterations exceeded, blah blah blah. So it doesn't work. Okay, but normally this is supposed to be better for fluids, but it didn't work. What actually worked then was this. Go to constant thermophysical properties. I make the density constant in this equation of state. Note that doing so will actually get rid of your ability to simulate natural convection properly, but it will help you in terms of solver stability. So you have seen the solver crash already. So 1, 2, and 3. Okay, next I will just give it a density of maybe 1050, for example. Okay, so basically what this means is that this is a polynomial expression of temperature, and these are the coefficients of each term in the polynomial. So this one is the coefficient of the t to the power of 0, or it's just a constant. This one is the coefficient of t to the power 1. This one is the coefficient of t to the power 2, coefficient of t to the power 3, all the way to the end. So what you note is that if you do it with a constant density, actually this thing will run. So I'll set the density constant to 1050 kg per meter cube, as you see there. And let me do a let me see, all run parallel, and let's run it again. Okay, MPI run with number. Oh wait, did I do an all run decompose parallel? Oh, did I? Oh yes, I just ran an all clean. Okay, no wonder. Let's do all run parallel again. Now I'll just run in the background. So it'll take a while again to decompose, and okay, so I'll just do a tail f log.buoyantPimpleFoam. And you can see that now this thing actually runs properly. Now this again is a promising result. It is not fully tested and everything, but it's actually pretty good compared to what we were seeing before. Now, of course, the caveat again I have to say is you're taking out the natural convection altogether, and that is actually pretty problematic. But it's better than nothing. There is some way that you can simulate forced convection, and that's actually good enough. And this is actually LES grid. Let me show you. Control-Shift-T for new tab here in Linux Mint. Let me show you the mesh. Okay, so let's see. Is that same mesh? Is the same mesh? Okay, never mind. Let me do system block mesh dig IDDES. You see that this mesh is a 36 by 79 by 158 times 36. This is a IDDES level mesh. So I can actually just make it smaller, even up to quasi DNS level. It should be able to run, technically speaking. Okay, so what is the level for DNS? 157. So 157 to the power of 3 is supposed to be able to run. Okay, so 157 to the power 3 is supposed to run, and how many cells is this? And this is a Kolmogorov scale simulation. I cannot simulate to the bachelor scales, but this is about 4 million cells. And well, with this new laptop and with Linux Mint, okay, actually I tried to have a laptop just for simulation of this DNS. It should be able to do it right. But anyway, take a look at the oh shucks. Now, yes, okay, but again, you can see there is some promise to this setting the density constant. It actually makes this whole solver a lot more stable. Now you see there are actually some errors here. So there are promising results. It is not fully tested, but you can see it's actually pretty good. Okay, so let's see. LS processor 0. Okay, I didn't get them to record all the time steps very rigorously. I can do that, but again, I'd say this is actually very promising direction to go. Okay, so let me copy this IDDES case 2 thermophysical properties blah blah blah. Promising experiment, IDDES constant density IDDES. So that I just label it as promising. It is not fully capable, but it's a promising case. Okay, so let me change it back here. So you can see that it's promising because we know where the instabilities are coming from. Okay, one of these sources is due to the density fluctuations in buoyant pimple foam. Of course, the other possibility for instability is due to the fact of the cyclic boundary conditions being very wonky. Because yeah. But anyway, I'll just stop for now. This is just the update that I have. I'll get back to you when I have something another update, I guess. If I get another update, there's no promises for that. Okay, so thanks for watching. I'll see you guys again. Bye bye.